Look at this piece of apparatus. Isn't it beautiful? This is an old-fashioned pressure meter. It's called a jolly bulb. And the bulb is this part here. It's got some air in it. And the air goes up this tube and then all the way down and then back underneath here, where on top of the air there is a cap of liquid mercury. And what happens is that when the air in here comes under more pressure, then it pushes the mercury up the tube, and you can measure a greater air pressure because the mercury has shifted up. And when there's less air pressure in here, it's not pushing the mercury so hard, and so therefore the mercury will sink down. And so this will give us a measurement of the air pressure, and what it can do is it can help us to see what happens when we change the temperature, what happens to the air pressure. Now, a modern day version of this equipment, that to my eye doesn't look nearly so good, is this digital one. And so it's reading the air pressure 9,800 pascals. And if I hold the jolly bulb in my hand, then what you can see is my thermal energy is transferring into the air inside here, and the pressure is actually going up. So what is the connection between pressure and temperature of a gas? Well, I think we should use this vintage apparatus to find out. So I have this vintage apparatus set up, and what I'm going to do is I'm going to put some water in here, and I'm going to measure the temperature with this thermometer, and I'm going to read off this linear scale where the mercury column has risen or fallen to. Now, an important thing is here that on this linear scale, it's not going to give me pressure in any ordinary units. It's not going to tell me what it is in pascals. So I need to calibrate this scale against the scale of pascals. And the way I'm going to do that, it's cheating a little bit, but I'm going to do it with this digital jolly bulb. The first thing I need to do is just record what the air pressure is like at the temperature of the water that has come straight out of the tap. So I've submerged my digital jolly bulb. Now my water out of the tap should be ambient. It should be the same temperature as the building, and in fact I find that it is. So the air pressure at the moment at the temperature of our water is 97.4 kilopascals. Now I'm going to record that on in a table here, so that my pressure in pascals was 97.4, kilopascals, 97.4. I've drawn a nice little table here, and we're going to record some measurements. The very first thing I'm going to do is now I'm going to take this water, I'm going to pour some of it in with our jolly bulb here, until it is submerged. And we'll just let that settle, and then we'll take the first reading. And the first reading from here on the scale, I think, is 77.1. So 77.1 for a temperature of, eye level, exactly 20 degrees Celsius. 20 degrees Celsius. So I've recorded it in a table that looks like this. I now plan to take 9 more readings up to the point where the water is boiling. So check back and we'll see how we've got on. First things first is we need to start heating the water. For that I need to turn the Bunsen burner on, so we'll do that straight away. And we will carry on as so. So there you can see I've plotted this graph and we have temperature on the x-axis, and I've got that jolly bulb scale in centimetres on this axis, and it goes from 76 centimetres up to 77.2. And you can see that as the temperature got hot, the number on the jolly bulb scale got smaller, but it got smaller in a linear way. There's a straight line being drawn here. It almost seems that as you change temperature, you seem to change pressure by the same amount. Now, because we now know that this is true, and we know that the starting pressure was 96.5 kilopascals, and the finishing pressure was 120 kilopascals, then applying that linear relationship will help us to see what happens when we go to even colder temperatures. So now you can see I've plotted the pressure here in kilopascals, and I've plotted the temperature here. Now these two data points here are just these two ones that we've got here. So the higher pressure at 100 degrees is there, and the lower pressure at 20 degrees is there. What I want you to notice is that when I join these two, the two go over here somewhere. And what it basically is showing us is that at a very cold temperature, and according to this apparatus at a minus 150 degrees, there would be no pressure anymore, because you can see that as it gets colder, the pressure gets less and less and less. Now, when scientists first realised this, they hypothesised that there must be a temperature at which the pressure goes to zero. So what does this mean then? Well, scientists with more accurate apparatus than myself had a go at this experiment where they measured the pressure at different temperatures for a gas. And they found that their data points meant that the pressure got less as the temperature was smaller and smaller. Now, what they did was they, just like I did, is they extrapolated these data points backwards. And the first thing they were interested in is what happens when you chase them all the way back over here. And in fact, what they did was just like this. That was not a very good line. But extrapolating it backwards took them to a temperature where the pressure went to zero. And that temperature in Celsius was minus 273 degrees Celsius. What does it mean if the pressure has gone to zero? Well, if you remember that inside the container, in this case the jolly bulb, which I, for confusing reasons, have drawn as a square, the particles inside collide with the container walls, exerting that pressure on them as they exert a force over that area. Now, what does it mean to have no pressure? It means that there is no force being applied to the walls. It doesn't mean that there's no air inside the jolly bulb. We know there is because it was there to start with and it hasn't gone anywhere. But what it now means is for there to be no force applied to the walls of the jolly bulb, then the air molecules inside cannot be striking the walls of the container anymore. You might think, well, how can that be? There are billions of molecules in there. How are they all not striking the walls of the container? And it's because they are stationary. What we have done is we've considered a temperature that corresponds to a kinetic energy of zero. The particles are not moving. And this means that you cannot possibly get colder than this temperature. It is the coldest possible temperature. A scientist called Lord Kelvin realised that the significance of this was really great, and that maybe instead of starting our temperature scale at 0 degrees Celsius, that we should start our temperature scale down here at the coldest possible temperature. And so he called this the Kelvin scale, or the absolute temperature scale. It starts with 0 Kelvin at minus 273. And then it goes up with the same increments as Celsius. So 1 Celsius rise is the same as 1 Kelvin rise. In fact, there is a formula that links the two temperature scales. So if I have my temperature in degrees Celsius, say for example minus 273, then what do I have to do to get the Kelvin temperature? Well, I have to add onto it 273, and this will equal my temperature in Kelvin. This is a nice way of just going between the two. Of course, I might want to go the other way as well, that the temperature in Kelvin, such as 0 degrees Kelvin, well, what is that temperature in Celsius? That is minus 273. And this gives us the temperature in degrees C. So, minus 273 degrees Celsius is equal to 0 Kelvin. Notice how the Kelvin doesn't have the degrees symbol in it, and that's a slight difference between the two. So that was the first major thing that they found from this study, that there is in fact a temperature where all of the particles have stopped moving, and it gave Lord Kelvin the opportunity to realise that there could be a much more useful temperature scale, the Kelvin scale. There's another reason why the Kelvin scale is useful, because there are no negatives in it. You can't have a negative Kelvin temperature. The coldest temperature is 0. But what it means is that if you double in temperature on the Kelvin scale, then the particles have doubled in kinetic energy. That the link is strong and it is there. And it doesn't work for the Celsius scale because of the presence of the 0. You can double from 10 to 20, but you haven't really doubled on the absolute scale. You've increased by about 8%. And so on the Kelvin scale, doubling in temperature doubles your kinetic energy. And in the gas laws, we must use temperature in the Kelvin scale. There's a second interesting thing that this data shows us. Because it is linear, it means that we can do some maths here. Maths that we describe as one of the gas laws. There are in fact 3 gas laws. The relationship between pressure and volume, Boyle's law, is the one in the previous video, but this law is different. It's pressure against temperature, Charles' law. And I need you to imagine this. First of all, we need to imagine what this gas law is actually telling us. This fire extinguisher is a gas, it's in a fixed volume. It means that this volume is not going to change. But what I want you to consider is how much pressure this gas is under inside here. Quite considerable pressure, as it turns out. And this is in here at room temperature. But what would happen to the pressure inside this if I started to increase the temperature? If I placed this pressurized canister in a fire, what would happen to the pressure inside? Well, it's going to go up. But how much is it going to go up? Well, we can work it out using one of the gas laws. So, the gas laws is as follows. If this is a linear relationship, then pressure of a particular gas is going to equal a constant of some sort times the temperature. Constant is the gradient of this graph in this particular example. But that's not the thing that's really interesting, because if I'm talking about the same gas, then what's going to happen is that for that particular gas, the pressure divided by the temperature is always going to equal that constant. Whether or not I've got my fire extinguisher at room temperature, or whether or not I've got my fire extinguisher in a fire, they're going to equal the same constant. The constant is actually, it's a mix of things that make that constant. For any given situation, that constant is a particular number. but from one situation to the next it might change. And it's really dependent on the volume of the container, the number of particles that you have inside. But if the pressure divided by the temperature always equals that magic number, both before in the cold room and afterwards in the hot room, then what we're going to find is that the situation before, which I'm going to call P1, which represents the pressure when it was in the first situation, well, that pressure divided by that temperature has got to equal the ratio of pressures in the second situation, the ratio of pressure to temperature in the second situation. Because it equals a constant and that constant stays fixed, the ratio of pressure to temperature before you heat it to the ratio of pressure to temperature after you heat it has got to remain the same, to the extent where we don't even need to know the constant. We know that this relationship holds true. So, say for example we want to use our actual data from this experiment. We found that the temperature of the first measurement here, well, it was 20 degrees Celsius. So what we need to do is we need to go through this formula to work out that temperature in Kelvin, because these have to be in Kelvin, remember? So 20 degrees plus 273 is 293 Kelvin. And so that is our temperature to start with. So 293, and the pressure as we measured it at that point was 96.5, so 96.5 kilopascals. So 96.5, there we go. That is the ratio of pressure to temperature for that first measurement. And our second measurement, P2, well, in this case we know what the second measurement was, but I'm interested to see how accurate we were. And we can do that with this. What I want to do is say what happened when we reached that second temperature, which was 100 degrees. So 100 plus 273 is 373 Kelvin. Now if you remember that the pressure here was at 120, well, what I can do now is I can put 373, and what I don't know is that second pressure. It was 120 kilopascals. But I want to see if the maths actually works out here. I haven't got my calculator. I never have my calculator. 1 second. Okay. Right, so this calculation here, we need to multiply this side of the formula by 373, because if you remember we have to do the same thing to both sides, and this is divided by 373, so we get rid of that by multiplying both sides by 373. So 96500 divided by 293 multiplied by 373 should give us 120,000. But does it? How accurate have we been? Well, only time will tell. So multiply that by 373. Nail biting. Oh, wowzers. So the pressure afterwards was 100, and we're waiting for 120, remember? It thinks 122,848. That's not so bad, because that actually works out as, let's just do, there we go. We were 97.7% accurate with our experiment. And so we can use this relationship as one of the gas laws for working out various different things. You've got to remember that the volume has to be the same on both sides. That is not something that's changed. It's just that ratio of pressure to temperature always stays the same. If you increase the temperature, you increase the pressure. So of the 3 gas laws, there's only 2 that you're going to need to know in equation form. And the very first one is the one that links pressure and volume, so Boyle's law. traditionally done with a pump and looking at the oil, and to see when you put something under pressure, its volume tends to decrease. Well, that gas law is written like this, that the product of pressure and volume is always the same. And so the product before you make a change is equal to the product after you make a change. But in the experiment that we've just done here, we have the ratio of pressure to temperature always stays the same. Charles's law. And so these two formula are worth knowing. There is a formula that might get you out of trouble that's not given in the exam, and it is this one. It's P1 V1 over T1 is equal to P2 V2 over T2. And what you can basically see is that that is an amalgamation of both of these formula. You look with this, and you can solve any question you like. If the temperature stays the same on both sides, then you can ignore it from the equation. If the pressure stays the same, you can ignore that, and same with the volume. The two things that do change, they can stay in the formula, and it'll help you predict that missing thermodynamic quantity that the question is asking for.